On the regression estimation, let's look at a very simple example, 3.20. A researcher, he collected data and he wants to see if there is any, how can we estimate the lung cancer. And he also collected data showing that smoking, X, variable X, shows a linear relationship with the lung cancer's data, Y. So in this case, assuming he plots the data showing the X and Y linear relationship, and he collects a set of data with a summary of X bar from the sample, the variance, the standard deviations of the X data, the sample average mean Y and SY, and also SXY. Assuming the population index start from 100 for the population X bar and also for the capital Y bar. Let's compare the ratio estimator and the regression estimator. Under the ratio estimator, the Y bar is equals to R times X bar. Then apparently we can estimate the ratio, that is comparing Y bar to X bar, is about 1.0593, and multiply to the population true value of X bar index 100, so that becomes 10593. How well is this point estimate to estimate the population average of lung cancer? We look at the variance of the Y bar or R times X bar obtained from the ratio estimator. Making use of all this data, we can find that this is about 332.2153 times the finite population correction factor corrected by the sample size. Okay, I'm not going through all the details with the calculation, but that would be a very good exercise for you to check. Next, with the regression estimator Y bar is equals to our sample Y bar minus slope, the beta, multiplied to the difference between the sample X mean and the population X mean. Beta is defined as the optimal beta, and by the least square formula is equals to SXY over SX square. In this case, that is about 1.0873. Rho, that is the correlation between X and Y, so that equals to SXY over SX over SY. So the correlation is quite high, it's about 0.716. The rho square is around 0.513. Now we can estimate our Y bar under the linear regressions is equals to 109 from the sample average minus beta multiplied to our sample X bar minus the population X bar. So we estimate Y bar under the linear regression, that's about 105.8468. As compared to the ratio estimation, it's very close. Now we can estimate our variance of the Y bar from the linear regressions, and this will be 1 minus rho square at the optimal variance, 1 minus rho square multiplied to the estimated variance of Y bar, which is around this is about 0.48 times 26.11 square. And we don't actually need to find out the finite population correction factor and the sample size, because what our aim is to compare the variance. Okay, so from the variance, the optimal from the linear regression, this is about 332, and the ratio is about 332.2153. So apparently the linear regression estimated variance is slightly smaller than the variance from the ratio estimator. So we can say that with our point estimate and the smaller estimated variance, we can use the regression estimator, which is slightly superior than the ratio estimator in this case. They have a smaller variance. Smaller variance, that means a smaller standard error or the smaller boundary error with our point estimate. Okay, so I hope that could help you to work on your assignment questions that usually, like I said during the video conference, usually in chapter 3, we would ask you about what the main purpose of simple random sampling, when or under what kind of situation we would apply simple random sampling, and then we would have some exercise on estimating the population mean, population proportion, or population total with the different estimator, and to explain about which one you would choose under different situation. Okay, so good luck on chapter 3. Next week we will continue on chapter 4 on the stratified random sampling.